Dear students, in this video, we will discuss the stability analysis of different methods. And for stability analysis, we will use this equation as the reference equation. Y dash is equal to lambda y, which is nothing but this is our function f of xy. And y at x naught is y naught. This is our initial condition. Okay. So first we will discuss about the stability of Euler's method. So we know that what is the Euler's method? Euler's method is given by yn plus 1 is equal to yn plus h f at x and yn. And since our function f of xy is lambda y here, for the reference equation we have selected this is as the reference equation for all the methods. Hence we can replace this f of x yn is nothing but lambda at yn. So f of x and yn is replaced by lambda yn due to this relation. Okay, now you can take yn common from here, so we will get 1 plus lambda h into yn. So this is our equation number 1. Now for stability analysis we will compare this relation yn plus 1 is equal to 1 plus lambda h into yn with this. We will comparing, so we will get this yn plus 1 is equal to e lambda h yn. So when you compare, so you will get e lambda h is nothing but this 1 plus lambda h. So e lambda h is 1 plus lambda h. That means this is the Euler's method is nothing but the numerical method of order 1. We have already discussed about in last class previous video that what is the first order method, what is the second order method. So this is the first order method. Okay, and we know that for absolute stability the magnitude of e lambda h should be less than 1 for absolute stability. So here Euler's method is absolutely stable if magnitude of e lambda h is less than 1. Now here we may have two cases. One, when lambda is a real number, so we have taken this case here A, and when lambda is a complex number, so we will take the second case. So now let us take the first case when lambda is real. So in that case this relation magnitude of e lambda h is less than 1 will give you this magnitude of 1 plus lambda h is less than 1. Now open this, then we will get this inequality minus 1 is less than 1 plus lambda h is less than 1, and hence we can say that lambda h varies from minus 2 to 0. So that's why we will get this interval lambda h belongs to the interval minus 2 to 0. So this is basically an interval. So this region, this is the region from minus 2 to 0. This is the region of absolute stability. Now here either lambda is negative, either lambda is positive. Okay, so suppose if lambda is greater than 0, if lambda is greater than 0, h is also a step size always positive quantity, so obviously their product will be a positive quantity. And in that case if lambda is greater than 0, then this method is always relatively stable. And we know that what is the condition of relatively stable? The condition was basically this. This was the condition. For relatively stable, this relation should hold. Magnitude of e lambda h is less than e raised to the power lambda h. Because lambda will be positive, h will be positive. So e raised to the power a positive quantity. So always this quantity will be a greater than, because we know that what is the value of minimum value of e, 2 point something, and this will be a positive quantity. So obviously we will always have a relative stable method. So in that case our method will be relatively stable if lambda is greater than 0. Fine. Okay, now the second case when lambda is a complex number. So suppose lambda is this, lambda r means the real part plus I lambda capital I. So lambda I means imaginary part. So here this is our lambda. Now we are taking this relation. So magnitude of e lambda h is less than 1, but e lambda h is nothing but 1 plus lambda h. So 1 plus lambda h is less than 1. Then we will replace this lambda by this relation lambda r plus I lambda I. So we will get magnitude of 1 plus h into lambda r plus I lambda I. This magnitude closes and then lambda less than equal to 1. So when we separate the real part and imaginary part, so we will get 1 plus h lambda r, this is the real part, plus iota h lambda I. This magnitude is less than 1. Okay, so when you solve this magnitude, then we will get square root of the real part, and it is a square, so 1 plus h lambda r whole square plus the square of imaginary part, that means h square lambda I whole square. This should be less than 1. Now squaring both sides, so we will get this relation 1 plus h lambda r whole square plus h square lambda square I less than 1. And this is nothing but basically a circle. This is a circular region. So this is the graph. Here this lambda r h, that means this part. So this is basically the real part, and this h lambda I is the imaginary part, and the center is obviously here from this -1 and from here 0. So -1 0 is the center. When you draw this, so we will get, and the radius is 1, so obviously -1 and 0. So we just draw a circle with radius 1 and center -1 0. So we will get this region. And see, here is inequality less than 1. That's why this is the shaded part. This is not just like the boundary of the circle. No, because less than 1 means inner part of the circle. So we will get the shaded part. So this is basically the region of stability of Euler's method if lambda is a complex number. So in real case, this is the region of stability. For complex case, this shaded part is the region of stability for Euler's method. Okay. Now we will discuss about the modified Euler's method. So what is the modified Euler's method? We have already discussed this method. So method is yn plus 1 is equal to yn plus h by 2 f of xn yn plus f of xn plus 1 yn plus 1. So this will be the modified Euler method. And since again our reference equation is this, so we will replace this f by lambda y. So when we are replacing this part, so we will get lambda yn plus, similarly here with the help of reference equation we will get lambda yn plus 1. Okay, so from here we will get yn plus 1 is equal to yn plus h by 2 lambda yn plus lambda yn plus 1. Now we can take yn plus 1 in the left hand side and the yn term in the right hand side. So we will get 1 minus lambda h by 2 yn plus 1 is equals to 1 plus h lambda by 2 into yn. So from here yn plus 1 is equal to, we can take this in the right hand side. So we get 1 plus h lambda by 2 divided by 1 minus h lambda by 2 into yn. So when you comparing with this relation, so we can say that this is basically your e lambda h. So this is your e lambda h into yn. Fine. So now this is your e lambda h. In this case, e lambda h is basically 1 plus h lambda by 2 divided by 1 minus h lambda by 2. Now for absolute stability, magnitude of e lambda h is less than 1. Okay, that means 1 plus lambda h by 2 magnitude should be less than 1 minus lambda h by 2. Okay, so when your lambda is negative, this is always true. Okay, when your lambda is negative, then what will happen? This will become negative sign and this will become positive sign. तो ये संख्या बड़ी होगी, ये संख्या छोटी होगी. So this will always be true, because h is always positive quantity. और lambda अगर for example say -2 तो क्या हो जाएगा? Then in that case what will happen? If you replace lambda is equal to -2, so we will get minus h should be less than, sorry, h, because lambda here I am taking lambda as -2, say. So what will happen? 1 minus h should be less than 1 plus h, and this is always true because h is always greater than 0, always step size. So this is always true. Hence when lambda is negative, this inequality is always true. Okay, so in that case we can say that from minus infinite to 0 is the interval of absolute stability, and this is derived by this lambda is less than 0 means from minus infinite to 0 on the entire half line from minus infinite to 0, half real line. So this is the interval of absolute stability. Okay, and this is called unconditionally stable because there is no condition. This is always true, that means there is no condition, no restriction. Okay, however when lambda is positive, then we will find with the help of, because we don't know exact lambda what at present here, so when we substitute the value, positive value of lambda, then we will find out the interval of stability. Okay. Okay, now the third method is the Taylor series method of order 2. So what is the Taylor series method? Suppose this y xn plus h. When you expand this with the help of Taylor series, we will get y xn plus h, y dash xn plus h square by factorial 2, second derivative at xn plus higher order terms, because here I am taking the second order method. So we will expand this up to second order, and rest of the terms are nothing but the error terms. Okay. Now we will replace these derivatives with the help of partial derivative of f, because our differential equation is this lambda this y lambda y. Okay, this is our f of xy. This is our reference equation. So with the help of derivative, substitute the values of derivative. So y xn plus h, y dash means what? Lambda y, or this is our f, so that's why f of x and yn plus h square by 2. Second derivative, we have already shown that the second derivative is nothing but this del f by del x plus, because when you differentiate this, so we have to take the partial derivative of f, so that's why we will get del f by del x plus f del f by del y at x and yn plus higher order term. This is the exact one. Now we will use the approximation. So approximation means this is replaced by yn plus 1 is equal to, this is replaced by yn plus f is replaced by lambda yn, so h lambda yn plus h square by 2 del f by del x, because what is f? In this case f is nothing but lambda y, function of y only, so obviously del f by del x will be 0, because f is a function of y only, that's why 0, plus f is nothing but lambda y. At point x and yn, its value will be lambda yn, and then del f by del y. So first partially differentiate f with respect to y, so we get only lambda, केवल lambda आएगा partial derivative, तो हमने यहाँ put किया value, plus higher order term, so order of lambda h cube. This is the approximation with the help of reference equation. This. So from here you can take yn common, so we will get 1 from here hy, from here lambda h square by factorial 2. Okay, and lambda into lambda will give you lambda square, so h square lambda square by 2 yn plus higher order terms. And when you remove this, so we will get the approximation formula. So yn plus 1 is approximately equal to this quantity 1 plus lambda h square by 2 yn. This is nothing but your e lambda h and into yn. So e lambda h here is 1 plus lambda square h square by 2. So basically this is a second order method. Okay. So now for absolute stability, magnitude of e lambda h should be less than 1. That means magnitude of 1 plus lambda square h square by 2 should be less than 1. Again here there are two cases, when lambda is real and when lambda is complex number. So when lambda is real, so we have already shown this in our previous video, that when you open this we will get this interval lambda h belongs to -2 to 0. Okay, when you open this and then find out the interval, then we will get lambda h belongs to -2 to 0 when lambda is real. Now when lambda is complex, so just like in Euler's method, when you open this you will get this type of structure. So I am not going in detail. So here we will get the real part h lambda r, because lambda is a complex number, so lambda is basically nothing but lambda is the real part plus I lambda I. This will be, so when you take complex number, so you have to substitute it here, then open this and then find out the interval. So this is very difficult to find out this, but ultimately what we will get the shaded part. So here is the real part h lambda r, here is the imaginary part h lambda I, and we will get this shape from -2 to 0. Okay, this we will get this type of shape when lambda is complex number. Okay, note for third order Taylor series method, because here we have taken the second order method. Suppose you are taking the third order method, then e lambda h will be nothing but 1 plus lambda h plus lambda square h square by 2 plus lambda cube h cube by 6. And when you again use this relation for stability, then the interval will be lambda h belongs to -2.51 to 0. सो -2.510 ये आपका इंटरवल आएगा व्हेन लैम्डा इज रियल. ओके, व्हेन लैम्डा इज रियल. ओके, now we will take the Runge-Kutta method, fourth method. Now Runge-Kutta method. So Runge-Kutta method, first take second order Runge-Kutta method. So the method will be yn plus 1 is equal to yn plus 1 by 3 2k1 plus k2. What is k1? K1 is equal to hf xn yn. Similarly, what is k2? K2 is hf xn plus 3 by 2 h yn plus 3 by 2 k1. Okay, again we will take this reference equation, y dash is equals to lambda y f of xy. So now what will be the k1? According to this, k1 will be h, f is nothing but lambda y, so that's why lambda yn. तो यहाँ हम पुट करेंगे तो अकॉर्डिंग टू दिस रिलेशन ये हो जाएगा लैम्डा yn. सिमिलरली k2 की वैल्यू निकालेंगे, k2 इज h lambda, what is your, because this is your reference equation, so f at some point is nothing but lambda of y. So lambda, what will be the y? According to here, this will be the yth coordinate, that's why yn plus 3 by 2 k1. क्योंकि y की वैल्यू, क्योंकि यहाँ lambda y है तो f of x, this is the x part, this is the y part, so this is your y, so that's why lambda yn. Okay, and now lambda yn plus 3 by 2, what is k1? K1 is this, so h lambda yn. From here you can take yn common, so h lambda 1 plus 3 by 2 h lambda yn. Now we have k1, we have k2, substitute these values herein, so ultimately yn plus 1 is equal to yn plus 1 by 3 2k1, that means 2h lambda yn plus k2, k2 is this, so h lambda 1 plus 3 by 2 h lambda yn. Now again you can take, you can simplify this, so what we will get yn plus 1 by 3 2h lambda yn and h lambda yn, so we will get ultimately, when we are adding this term and this one, we will get 3h lambda yn plus multiply these two terms, so we will get 3 by 2 h square lambda square yn. Now you can take yn common from here, ultimately yn is also here, so ultimately when you take yn from the complete term, then we will get 1 plus h lambda plus h square lambda square by 2 yn. So this is your, basically this is bracket quantity is basically e lambda h yn. So ultimately again we will get the second order method, so e h lambda is 1 plus h lambda plus h square lambda square by 2. Now for absolute stability, this is the criteria, magnitude of e lambda h should be less than 1, that means 1 plus lambda h plus h lambda square h square by 2 should be less than 1, and we have already discussed this part. Okay, so in case of when lambda is real, again we have two cases, when lambda is real, when lambda is complex. When lambda is real, the interval will be lambda h belongs to -2 to 0, because when you open this, we have already discussed this in our previous video. You can see our previous video where we have already discussed about the second order approximation. Okay, so this will be the interval, and when this is the complex, when lambda is complex, that means lambda is lambda r plus I lambda I, then again we will get this part which we have already taken here for Taylor series method. This and this both are same. Okay, so ultimately when lambda is complex, this shaded part is the region. Okay, so this is basically the Runge-Kutta method of order 2. Now we will take the Runge-Kutta method of order 4. So this will be the method. So yn plus 1 is equal to yn plus 1 by 6 k1 plus 2 k2 plus 2 k3 plus k4. What is k1? K1 is hf xn yn. What is k2? K2 is hf xn plus h by 2 yn plus k1 by 2. K3 will be hf xn plus h by 2 yn plus k2 by 2, and similarly k4 will be hf xn plus h yn plus k3. Okay, again we will take this as a reference equation, y dash is equal to lambda y is equal to f of xy. Now find out k1, k2, k3, k4. So k1 is according to this hf, but f is here lambda y, that's why k1 will be h lambda yn. Now find out k2. So k2 will be h and then f, but here f is lambda y, that means yth part, so we will multiply this quantity by lambda, so lambda this quantity yn plus k1 by 2. Okay, so now but k1 is lambda h yn, that's why h lambda into yn plus h lambda yn by 2. You can take yn common, so we get h lambda 1 plus h lambda by 2 into yn. Now find out k3. K3 is h f is this, according to this f will be nothing but lambda yn. So lambda yn means this part, yn plus k2 by 2. So yn plus k2 by 2. K2 we have already evaluated, substitute the value. So h lambda yn plus h lambda by 2, 1 plus h lambda by 2 into yn. Again you can take yn common, so we get h lambda 1 plus h lambda by 2 plus h square lambda square by 4 yn. Now find out k4. K4 will be h lambda into this h, but f is again lambda yn, so yn part is this. That's why h lambda yn plus k3, and we have already evaluated k3, this k3, so substitute it here. So h lambda yn plus h lambda 1 plus h lambda by 2 plus h square lambda square by 4 into yn. Again you can take yn common, so we get this h lambda 1 plus h lambda plus h square lambda square by 2 plus h cube by lambda cube by 4 yn. Now substitute this k1, k2, k3, k4 herein. So what we will get this, yn plus 1 is equal to yn plus 1 by 6. This is your k1. K1 is this, k2 is this, k3 is this, and k4 is this. When you simplify this, and from each term you can take h lambda yn common, h lambda yn, h lambda yn, h lambda yn, and similarly h lambda yn. So ultimately you can take h lambda yn common, so we will get 1 plus 2, 1 plus h lambda by 2 plus 2, this 1 plus h lambda by 2 plus h square lambda square by 4 plus 1 h lambda plus h square lambda square by 2 plus h cube by lambda cube by 4, and this whole bracket is multiplied by h lambda yn. When you simplify this, so we will get yn plus, because here is yn, here is yn, you can take yn common, so that's why yn, and then 1 plus h lambda plus h square lambda square by 2 plus h cube by 6 plus h4 lambda 4 by 24. Okay, so ultimately this bracket quantity is your e lambda h, and this is your yn. So e lambda h is 1 plus lambda h plus lambda square h square by 2 plus lambda cube h cube by 6 plus lambda 4 h4 by 20. So this is a fourth order method. Okay, now for absolute stability, this is the criteria, magnitude of e lambda h should be less than 1. Now again we have two cases, when lambda is real, when lambda is complex. When lambda is real, then after simplification, because this is very difficult to solve this manually, that's why after solving this, what will be the interval? Lambda h belongs to minus 2.790. This will be the criteria. Now when lambda is complex, that means lambda is lambda r plus I lambda I. When we will take this as the complex part, then we will get this shaded part. This is a little bit different from the previous one. In previous one we are having this type of shaded area. However, here you will see that we are having this type of area. This is little bit different. Okay, here we have minus 2, here we have minus 2.79. So this will be the shaded part, is basically the area when lambda is complex. So this is lambda RH, lambda IH. This point is 2.83, this is 0, and this will be obviously minus 2.83. Here is minus 2.79. Okay, so this will be the area. Now in the next video, I will discuss few more examples, few more general examples for stability. Okay, thank you.